Oxygen sensors, also known as lambda sensors, are critical components in internal combustion engines. They measure the amount of oxygen in the exhaust to help the engine control unit optimize the air-fuel ratio. This ensures efficient combustion, reduces emissions, and maintains engine performance. Modern vehicles, especially hybrids, may use multiple O2 sensors per bank for upstream feedback and downstream catalytic converter monitoring. In electric vehicles, they are obsolete. O2 sensors are essential for optimizing engine performance in traditional vehicles. O2 sensors come in various wiring configurations, primarily differentiated by the presence and type of heating element. These include one-wire unheated sensors, which are rare in modern vehicles due to slow warm-up. Two-wire unheated sensors have a signal wire and ground. Three-wire heated sensors include signal, heater power, and ground for faster operation. Four-wire standard heated sensors are the most common, with signal and heater circuits. 5 to 6-wire wideband sensors provide more precise measurements and are used in advanced systems. The number of wires reflects the sensor's complexity and functionality, particularly regarding its heater circuit. While wire colors can vary by manufacturer, some industry norms exist for O2 sensor wiring. Signal wires are often white for upstream sensors, carrying high-voltage 0 to 1 volt signals to the ECU. Downstream signal wires are typically black with lower voltage. Heater circuit wires include gray for heater ground and black for heater power at 12 volts from the battery. Ground wires are frequently black or white, and this pin diagram shows a typical 4-wire setup. When replacing sensors, match cable colors as shown here for OE versus Denso sensors. Always refer to the vehicle-specific manual for accurate wire identification, as colors are not universal. This electrical diagram shows the heater and sensor elements with ground connections. The heater circuit in O2 sensors is essential for rapid and accurate operation. It heats the sensor's zirconia or titania element to its optimal operating temperature of 300 to 400 degrees Celsius quickly, preventing condensation and ensuring accurate readings within 20 seconds of startup. Heater circuits typically draw 0.5 to 2 amperes from the battery to reach this temperature. A faulty heater circuit can trigger the check engine light and OBD2 codes, such as P130 through P0167. The heater circuit connects through specific wires in the sensor's wiring harness, as shown in this schematic. The signal wire connects the O2 sensor to the vehicle's ECU, providing crucial feedback for air-fuel mixture adjustments. The sensor's tip contains a zirconia element that generates a voltage differential when exposed to exhaust gases compared to reference air. This voltage signal, ranging from 0 to 1 volt, is interpreted by the ECU to determine if the mixture is lean or rich. This enables real-time fuel trimming and optimizes engine performance. Wiring issues are the leading cause of O2 sensor failures. Common problems include electrical shorts, open circuits, and corrosion, particularly affecting the heater circuit. To diagnose these issues, use a multimeter to test for continuity, voltage, and resistance. The heater circuit should measure 2 to 20 ohms of resistance. Faulty wiring can trigger false OBD2 diagnostic codes and cause incorrect engine behavior, leading to poor performance or increased emissions. For accurate diagnosis, always trace the electrical circuits and refer to the vehicle's wiring diagrams. Modern O2 sensors incorporate digital signal processing, enabling direct communication with engine control units through protocols like CAN bus. Sensors now integrate with artificial intelligence and Internet of Things technologies for predictive maintenance, analyzing data to forecast issues before they occur. In hybrid vehicles, O2 sensors play a crucial role in monitoring the efficiency of the internal combustion engine component. There's increasing emphasis on low-emission sensors, constructed from recyclable materials to support environmental sustainability. O2 sensors are being developed for alternative fuel applications, particularly hydrogen fuel cells, where they help monitor oxygen levels. While O2 sensors remain vital for internal combustion and hybrid vehicles, their role will likely diminish as electric vehicle adoption increases. Future innovations may include self-healing ceramics, wireless sensors, and quantum sensors for enhanced durability and performance. Long-term, solid-state alternatives could replace traditional zirconia types. Rising repair costs may also boost the aftermarket diagnostics sector.